Hi everybody. The next section is on 5.2 on properties of rational functions. Now we've looked at rational equations before, and rational functions will be a little bit different in the sense that they won't be equations, they'll be expressions. So a rational function is basically something where you're taking a polynomial divided by a polynomial. So your book will define a rational expression as some polynomial which we'll call p of x divided by q of x. So an explicit example would be something like maybe where you've got x squared minus 1 divided by, say, x plus 2, something like that. Again, something where you have a polynomial divided by another polynomial. So one thing we want to look at, first of all, is finding the domain of a rational expression. So remember, the domain of a function or an expression is the numbers you can plug in for x or the independent variable, whatever it might happen to be if it's not x. That will basically tell you what the corresponding y-coordinate is. So remember that if something is not in the domain, you essentially don't know what the y-coordinate is that corresponds to that x-coordinate. And essentially what that means for rational functions like this is that if there's any number that you plug into the denominator that makes the bottom 0, then it's not in the domain of the expression. So for something like this, what you're basically looking at is you're just looking at the bottom. You can completely ignore the top and ask yourself, well, what number makes the bottom 0? And sometimes you can just see it like this one probably, but if you don't, you can just set the bottom equal to 0 and solve the equation. So in this particular case, if you set the bottom equal to 0, x plus 2 equals 0, if you solve that for x, you get x is negative 2. And remember, the idea is the domain is everything except for x equals negative 2, because you're not allowed to plug negative 2 in. I don't recall if I mentioned this earlier, but and you might think this is sort of an esoteric thing that you don't have to worry about, but in with modern computers and things like that, you do have to worry about division by 0. In fact, I remember reading an article once about a U.S. naval aircraft carrier that was basically shut down because the computer divided by 0. If you're interested in knowing more about that, let me know. But you can just do a search for, I think it was called the Smart Ship program. If you just do a search on Google or something for Smart Ship or USS Yorktown or division by 0 or something like that, it should tell you about it. But basically what it was is that there was this computer program that was supposed to enable U.S. naval ships to sail around the Earth's oceans without any crewmen on board, but things didn't quite work out as they had planned. So that's one thing we want to look at, is the domain of a rational function. That's basically what will make the bottom 0 is not in the domain. So one thing we want to look at then is graphing rational functions. Let's start out with a simple one. And again, the idea in this case is you may be expected to do something like this, say perhaps on the final without a graphing calculator, without a graphing tool. But let's say, for example, you wanted to graph something simple like 1 over x squared. Right? Well, what does the graph of that look like? Well, again, you can just sort of plot points if you want. You could do an xy table. And notice that this is a rational function, right? You've got the polynomial 1 divided by the polynomial x squared. And you would just plug in different values for x and see what you get. But that can be kind of difficult, especially because these rational functions have some weird behavior, especially, again, where you divide by 0. You can essentially think of dividing by 0 as basically giving you an infinite value for y. And so what you'll see happens here is that if you pick values closer and closer to 0 for x, you'll get that the y-coordinate is larger and larger. So rather than doing that, you can just kind of think of it that way. And the idea is, think of it this way: as long as whatever number you plug in for x, since you're squaring it, the bottom will always be positive, and so will the top. So the idea basically is, if this is your Cartesian coordinate system, the graph of this function will look something kind of like this. As x gets bigger, you're going to be dividing by a larger and larger number. So you've got 1 divided by a larger and larger number. So it will get closer and closer to the x-axis as you move out further in both directions. However, it won't ever actually be equal to 0. And then when x gets closer and closer to 0, you're going to be dividing by a smaller and smaller number, which means the y-coordinate will get larger. If you think about sort of that stuff on variation, right, this is sort of an inverse equation, right? The idea is the bigger x gets, the smaller y gets, and vice versa. The smaller x gets, the larger y gets. So the idea in this case is you can talk about sort of what's known as a limit, and you would say that the limit as this function approaches x equals 0, y is equal to infinity. It talks about that on the bottom of page 345. That's not something I'm going to emphasize, but you might encounter the limit concept as you get into calculus. You can also use transformations to graph these sorts of things. Like I can take the same function and I can do some sort of transformation. Like, for example, I could take and put an x plus 3 squared in the bottom, and then, for example, add 5. So if you think back to that stuff on transformations, that's going to take the previous graph that we had that looked like that, and it's going to shift it 3, remember, to the left, and then up 5. Right? So remember, this does the opposite of what you would expect. Instead of shifting it over 3 to the right, it shifts it 3 to the left. So all that stuff we learned about transformations will apply to these functions as well. I should mention incidentally that that line that the graph approaches this way and this way, I think I mentioned this before, are called asymptotes. So a line that a graph approaches but never quite crosses, or maybe crosses a finite number of times, is called an asymptote. So essentially what you can do to find the vertical asymptotes of a rational function is determine where the bottom is 0. That's where the graph is going to kind of shoot up. So just to give you another example here, and you can use that to help you graph these rational functions. You know, if I give you something like, let's say I give you a function, say g of x equals x squared minus 9 all over x squared plus 4x minus 21, something like this. Again, you're looking at where the denominator is 0 if you're looking for your vertical asymptote. Sorry, that 4x didn't look very good there. So essentially what you want to do again is find the domain of the expression, take the bottom and set it equal to 0. And so you can factor this into x plus 7, x minus 3. And so you'll see that you'll get vertical asymptotes at 7 and 3. So if you were to graph this function here, you'd get a vertical asymptote at negative 7. So you'd get something like that over here. And then you get another vertical asymptote at 3. You can also determine other things, like, for example, if the function is equal to 0, right, if you're looking for the y-intercept, you would make that 0. Remember, a fraction is equal to 0 only if the top is 0, so you should see that this graph will pass through the x-axis at 3 and minus 3, because that's where the top is 0. So for example, over here, and then I guess you'll get sort of weird behavior here at 3, but you'll see that the graph will pass through there, and so you can get information like that to try and draw basically a graph of one of these things without a graphing calculator. Now a graph can also, like this, can have horizontal asymptotes, not only vertical ones. And basically, what determines that is the power of the top versus the bottom, the numerator versus the denominator. So think about it this way. The idea is, as x is getting larger and larger, what happens to the height of the function? Does it shoot up forever? Does it level off to some height? Does it go down to 0? That will largely be determined by the leading coefficients of your two polynomials here. Because remember, like we talked about earlier, it's really the leading coefficients that have an effect on the behavior as x goes further out and towards infinity or negative infinity. So basically what will happen is, think about it this way: if the degree of the top is smaller than the bottom, x squared is going to be way larger than x when x is, say, at 1 billion. And so the idea in that case is that the bottom will be relatively large compared to the top, and if you divide a small number by a large number, you get something that's close to 0. So if the degree of the top is smaller than the bottom, the graph will approach 0. Now if the degrees are the same, like the original thing I had here, again, you can sort of imagine there's a tug of war between the top and the bottom. If the degrees are the same, essentially there will be a tie, and the tie will be that you'll take the coefficient of this divided by this. So in this particular case, you'd see that you'd get a 1 here and a 1 here, so this graph should level off to 1 divided by 1, or just 1. So if, for example, the leading coefficient here was 2 and it was 3 there, then that graph will level out to height 2/3. And then lastly, the third thing that can happen is the degree of the bottom could be less than the top, say maybe where you've got say 4x minus 21 on the bottom and x squared on the top, in which case, since x squared is larger than x, as x gets larger, the graph of that will approach infinity. Now, there are several different ways that it can approach infinity, and we'll talk more about that later on when we talk about oblique asymptotes. So basically, just to kind of give you an example here, let's try and graph one of these functions, or at least get some idea of what the properties of these functions will look like in this case, and then we'll talk a little bit more in the next section about actually how to graph them. But let's say for example, I give you let's say the function, say g of x equals 2x to the fifth minus x cubed plus 2 divided by x cubed minus 1. So the idea in this case is, let's say we want to find the horizontal or oblique asymptote for this one. I guess the vertical asymptotes would be where the bottom is 0. Now, the only real number you can plug in there that will make the bottom 0 is 1. So you would see when x is equal to 1, you get a vertical asymptote. The graph will either do this or go up on one side, down on the other. Again, we'll talk more about the graphs of this in the next section. But what we're mainly concerned with is what's happening with the horizontal asymptote. Now, because the degree of the top is larger than the bottom, you'll see that the graph will shoot off to infinity, but we can even get more information about that. We can also tell sort of how it approaches infinity, and that is, you can do that by basically taking the polynomial on top divided by the polynomial on the bottom. So you can take 2x to the fifth minus x cubed plus 2 and divide that by x cubed minus 1. Now, remember that if you have missing powers in there, you really should be putting them in. So let me put in a 0x squared and a 0x here. And then here, let me put in a 0x to the fourth and then a 0x squared. Let me scoot that 2 over. And then we'll put in a 0x there. So the idea then is you can go ahead and divide this out. So I guess you would multiply 2x or x cubed by 2x squared to get 2x to the fifth. So multiply that through. You'll get 2x to the fifth, and then you'll get, I guess, plus 0x to the fourth, plus 0x cubed, and then you'll get 2x squared times 1. That'll give you minus 2x squared, and then just go ahead and subtract those. So you'll get 0x squared minus a negative 2x squared, which will give you 2x squared, and then plus 2. And then, again, that's all the further you can go. The degree of this is 2, which is less than 3, so you can go ahead and stop there. And then the idea in this case then is that you'll get that the remainder in this case will be 2x squared minus 1. I don't see, am I making a mistake here? Oh, I'm sorry, I forgot to bring down my negative x cubed here, I'm sorry. So I guess you can continue, right? So then go ahead and keep going here. I guess you want to multiply x cubed by negative 1, so you'll get negative x cubed plus 0x squared, and then eventually you'll get negative 1 times negative 1, which is a plus 1. Again, subtracting and changing the signs, you'll get a 2x squared plus 1, because you'll get 2 minus 1 there. So the idea in this case then essentially is that this original function, the g of x, if you divide, can be written as the quotient, which we just got, which was 2x squared minus 1, plus the remainder, which we saw is 2x squared plus 1, divided by the thing we're dividing by, which is x cubed minus 3. So in other words, this function can be rewritten this way, And then the idea then is as x gets larger and larger, since I'm dividing a smaller power here by a larger power, this eventually will get closer and closer to 0 or disappear. And so the idea then is as x gets larger, the graph of this will approach the graph of this. So the idea is, like I said earlier, the graph will approach infinity, right? The idea is this degree of this is higher than that. It will approach infinity, but the question is, how does the height approach infinity? It will approach infinity along this graph, right? And the idea is that's the graph of a parabola, just shifted down one and stretched out by a factor of 2. So you should see that the graph will sort of follow that parabola out. Now, that may not make a lot of sense right now, but we'll see later on in the next section when we actually get to graphing these things, how that will help us graph them. Right? But the idea basically is that if you're looking at vertical asymptotes, you're looking at where the bottom is 0. If you're looking for horizontal asymptotes, right, asymptotes that run this way instead of up and down, you compare the degree of the top to the bottom, right? If the degree of the top is larger than the bottom, the graph will approach infinity as x gets larger. If the degrees are equal, there's sort of a tug of war between the top and the bottom. There will be a tie eventually, and that will level off to whatever the coefficient of this over that is. And then the third thing that can happen is the degree of the top is smaller or is larger than the bottom, smaller than the bottom, in which case the height of the graph will level out to 0. All right, well, I hope that makes sense. So if you guys have questions, make sure you ask. I know we're kind of getting into material that you guys might not have had before. So if you have questions, don't be afraid to contact me. All right, good luck.